As we start the second semester, we will begin taking a look at physics regarding motion, as you see there, position, velocity, acceleration, and momentum. These are some of my favorite topics of this class. I like the periodic table. I like what we've done before with the phases of matter, but we're in the physics unit now, and those are among my favorites, and that's because I really like this right here. And as I've said many times before, the class gets mathematical, and as we go through these next few chapters, expect to do a lot of this right here. So let's begin talking about position, velocity, acceleration, and momentum. Sections 11A and B. Ready to begin. Motion, the study of motion, we call mechanics, and that's really all mechanics is, the study of motion. We're not talking about the people who fix the cars. We're talking about studying motion. We call that mechanics. There are two main components. One of those we'll look at in this section in some detail, and the other one we'll look at a little bit later on. We will look more at kinematics this time, how things move. And then a little bit later, and I mean a very little bit later, we will look at dynamics, why things move. Chapter 11 is about kinematics, how, and chapter 12 is about dynamics, why things move. So now, are we ready? Here we go. You see this gentleman here on the train. Looks like he might be going on a business trip, has his briefcase ready and everything. Now he's looking out the window, and let's just say his wife is standing out here somewhere. Now the train starts to pull away. Our brains know exactly what's going on. The train is actually moving, but his eyes don't really realize that. It might be hard to see the picture on the screen, but the gentleman's eyes right here. To just his eyes, he may see that his wife is actually moving further and further and further away from him. And then to her eyes, he's moving further and further and further away from her. Well, what they each have is a point of view that we call the frame of reference. The point of view is based on the viewer. Now, we know for sure in our brains that the train is the object moving, and since he is standing in the train and attached to that train car, his body is actually moving away. But again, his frame of reference, to his eyes, his wife is the one that is pulling away. That may sound strange, again, because we know what's really going on, but you have to consider just the eyes from that point. So who's moving, the bystander or the train rider? Each one's eyes perceives the other person as moving away, and we call that frame of reference. Ready? What is a physical system? Well, we get to define the system as anything we want. We get to set the boundaries. So let's just say this classroom is our system. I can observe anything that is in the classroom, and something that's not in, that comes in, I can then observe. So people in the hallways making sounds, if those sounds come into the room so I can hear the sounds, then those sounds become part of our system because we can observe. So the system is anything within a given boundary, and we get to set that boundary ourselves, and then we can study all objects or sounds or types of energy that fall within those boundaries. And then we can use that information for whatever purpose we need. The system is anything within the boundaries, and we get to set the boundaries, and we can study anything that comes within those boundaries. Ready? Now, distance and displacement. Now, before I put any words up here, I'm going to take a moment to talk about the greatest sport ever invented, and that is baseball. Now, you have to pretend I draw well, because you know I don't. Okay, so I'm at bat right here. I get a base hit. Here's first base right there. Now, on a regulation-sized baseball field, that's 90 feet. Now, so far, I have traveled in only one direction. And you see the words distance and displacement. As long as those are in the same direction, then they're equal to each other. So I have traveled 90 feet, and my displacement, how far away from my starting point, is also 90 feet. All right, here comes the next pitch. I steal second base, and I make that safely. I have traveled another 90 feet. Now here's the thing. If I had a little step counter that counted how many feet I've traveled, I would go 90 and 90. That is 180 feet. However, on second base, I am not 180 feet from home. What I have to do here is the Pythagorean theorem. Because I'm talking about a straight line from home plate to second base. And if we work the Pythagorean theorem, we're going to end up approximately 127 feet after I round off to the whole number. So my distance traveled is 90 plus 90 is 180. See, if we were to drive a car and the road curves like this, let's say we've gone 90 kilometers, and then we turned north and we've gone another 90 kilometers, even though it's the same road, it just curves. Our displacement would be the straight line from where we started to where we finished. All right, so I can take that off now. Hey, here's a wild pitch. I scamper another 90 feet. Okay, now we can take that off because we're not dealing with it anymore. I have now traveled 90 plus 90 plus 90. So my distance traveled is now 270 feet. But my displacement at third base, that's how far from home I am. My displacement is 90 feet northwest if this was north up here. You see the difference? Distance is the total regardless of what direction. Displacement is when I stop moving, how far away from the starting point am I? All right, next batter hits a sacrifice fly to the outfield, left fielder, so I'll put an SF7 in the scorebook, and I end up scoring that run. Now, when I touch home plate, I am right back here where I started. I can erase this now. That's another 90 feet. I have traveled 360 feet in all directions on the baseball field. But my displacement, this is distance, but my displacement now is 0 because I am right back where I started the moment I touch home plate. Even though my step counter would go to 360, displacement is where I end up and how far from the starting point I was. So now here are the definitions. Displacement is a change in position after completing the motion. So when I was at home plate, I've gone all the way around the bases. My motion is now stopped. I am 0. But distance is the total that I traveled, 90 feet in 4 different directions. That was 360. Let's talk about this right here. The delta, you're going to see on the next line I put up. Delta means a change. Well, you consider the XY graph. But since we have just X right here, let's just go in that direction on the XY graph. Let's say we start here. All right, and we go this way. Okay, this is Vector Boulevard. I've gone 10 miles. That is all one very long road. So now, to go from here to here, here's my new starting point that I'm going to call position I. Initial position, XI. X is position, I means initial. And then I'm going to drive, let's say I drive 20 miles from here. That means I'm 30 miles away from where I started. So I made a stop here 10 miles away. I've gone another 20 miles to give me 30 miles away. Now I'm done. What I want to know is what's my change in position between these 2 points. And all I have to do now is subtract the 2 values and I will get 20. And I said miles, so I'll put my unit miles there. So displacement is one direction. And you see this word vector here I'm going to define in just a moment. That little triangle is a Greek letter delta. The name of that little triangle is delta. The definition is a change in a quantity, and we'll see that delta with other quantities as well. In this case, the quantity is position. So whenever you see delta, that means something has changed. X means position. Our distance has no direction because I can go in a distance any way I want. Okay, I'm going to back this up for just a moment here and show you again something I kind of drew a little while ago. So to get home from school, here's what I have to do. I have to go on one road, then get up onto the interstate, and that interstate comes down here, crosses the river on the Buckman Bridge, and then I make some other turnoffs before I get home. Well, if I look at my odometer, here's school, and here's home. If I check my odometer, I have gone approximately 20 miles will be added on to that odometer. However, remember, displacement means a straight line. How far away am I in a perfect straight line? That's going to be less than 20 miles. I think it's closer to 15 miles. But because I've had to change directions and go around a big curve, more distance, but displacement is this one straight line direction only. Okay, I had a change in quantity, a change in my position. If that was on an XY coordinate graph, well then I could do a right triangle and a Pythagorean theorem to calculate that distance. Distance has no direction, so we call that a scalar quantity. But displacement does, we call that a vector. Scalars are simply measurements without a direction. And that definition is coming up in a little bit. Vectors are measurements put into a particular direction. And that's why I have the colors up there so you can help remember. Scalar, no direction. Distance is a scalar. Displacement has a direction. You saw me write northwest on the baseball field a few minutes ago. Displacement has a direction, and anything with a direction is a vector. Ready? And here are the definitions here. I forgot to put the little transitions up, but that's okay. When I do a measurement, such as 25 kilometers, that is a distance. All I have is the number 25 and the unit kilometers. I did not put a direction. So a number and unit, as you see in the definition there, is called a magnitude. Since there's no direction, we call this a scalar. So distance is a scalar. Speed is a scalar. 65 miles per hour does not include a direction. So speed is a scalar. But now, look what I did with the green word vector there. A magnitude and a direction. If I go 25 kilometers in any direction, I chose north, then I have what's called a vector. Now I don't have to say north. I can say north, south, east, west, northwest, northeast, or I could say something like 25 kilometers towards Daytona. As long as I give any kind of a direction, I now have, in that case, the distance becoming a displacement. Or I talked about speed a moment ago. If I say I'm driving 65 miles per hour, that's a speed. We have no idea what direction. But if I say I'm driving 65 miles per hour south or 65 miles per hour towards Daytona, then I have a vector that's called velocity. And see what I'm doing with those little audio clues. Speed is a scalar and velocity is a vector, and a vector has direction. And we indicate a vector by using an arrow. So if you see an arrow above a quantity, that means that quantity has a direction, and that quantity is a vector. Most of the quantities we'll deal with in these physics units are vectors because they include direction. Ready? I mentioned speed just a moment ago. Obviously, you know what speed is, how fast an object is moving, and that is the definition of speed. And we calculate speed by doing distance over time. Speed equals distance divided by time. You're going to see that equation up here in just a moment here. We cannot stay at a constant speed, however. You're in the car and you're going to drive from Jacksonville to Orlando. There will be times you'll have to go faster and other times you'll have to slow down. And even if you try to stay at the same speed, well, you have to slow down because the traffic in front of you is slower. Or even if you put on cruise control, if the road slopes downward, your car will pick up some speed. And when the road slopes upward, your car will lose a little speed. And then, of course, you get off the highway onto the streets, you have lights you have to stop for and then speed up again. So it's pretty much impossible to stay at a constant speed for the entire trip. And even walking, we have to start and come to a stop. So we have to calculate the average speed by simply doing V equals D divided by T. Now in physics, V stands for either velocity or speed. And then if we have a direction, we call it velocity. And it's a very simple calculation. Let's say we walked 21 meters and we did so in 3 seconds. That would be walking fast or a light jog. What we simply do is 21 divided by 3 is 7, and we have the unit meters per second. Very similar to miles per hour, meters per second. Look, distance over time. Distance divided by time, meters distance divided by time, seconds, that's your unit. In this class, to get the answer completely correct and get full credit, you must put the correct unit in addition to the correct number. So 21 meters in 3 seconds, just divide and get 7 meters per second. And then if I know the speed or velocity and either the distance or the time is missing, I can do a little bit of pre-algebra and get the missing number, and we will do practice problems. Ready? Velocity is simply speed in a direction, and because of a direction, here we go again, velocity is a vector. Speed and direction are included. That's 65 miles per hour, that's a speed. 65 miles per hour north, that's a velocity. Anytime we add a direction, we have a vector, and velocity is one kind of vector. Now, can speed ever be negative? Can we go below 0 miles per hour? Can I drive negative 10 miles per hour? No, but I can have a negative velocity, and the negative sign simply means opposite direction. So let's say we want to go in this direction. We come up here and we want to turn right, but we get messed up and we end up turning left instead. Well, right would have been the positive direction because that's the direction we wanted to go, and negative would be the opposite. Now with a straight number line, that makes sense. To the right is positive, to the left is negative. However, let's say we were supposed to turn left and we just lost track of what we're doing. Left is the positive direction because that's the desired direction. And we end up turning right instead. In that case, that direction would be negative. Okay? Usually we consider up as positive. But if we're in the elevator, let me come over here, more room. If I'm in the elevator and I want to go down, let's say I'm on the 10th floor, and I want to go down to the basement or the first floor, well then down would be positive because that's the desired direction. But somebody hits the button on the 13th, actually there is no 13th floor in many hotels, 14th floor, because 13 is supposed to be a bad luck number. Someone on the 14th floor hits the button first, that elevator is going to go up. Well, that is negative to us, remember frame of reference, because we wanted to go down. So in vector velocity, the desired direction is positive, and the opposite direction is negative. Not just a wrong direction. If I want to go that way, well, this way is wrong, this way is wrong, and this way is wrong, but there's only one opposite. That's positive, that's negative. There's only one opposite direction that we can call negative. Ready? Okay. Adding velocity. Let's say we're going on a straight line. We make a stop and then we continue on, as I started to show a moment ago. As long as we're going in the same direction, we're simply going to add the numbers together, meaning this. Okay? We're going to take a long trip. Now, obviously, roads curve, but for our example, we're going to stay on the same road. Okay, starting point here. Okay, here's start. We're going to go 720 kilometers per hour west, which is this direction here. And this is our stop number 1. And then, same road, we continue on and we go another 83 kilometers west. So that's 720 and that's 83. Common sense, since we continued in the same direction, we're simply going to add these two numbers together. 720 plus 83 is 803. Our velocity and our displacement is 803 kilometers per hour west for velocity. Okay, does that make sense? As long as they're going in the same direction, we simply add them together. Now, to add, just like in algebra, we have to have the same units. We can't add two different units, just like we can't add x plus y. They have to be exactly the same units to add or subtract. Ready? Now, what if I'm going in one direction and I make a stop and then I come back the way I started? This time we're going in the opposite directions. So one way is going to be considered positive and then the opposite direction will be negative. So what we'll do is we'll either add the negative for the second value or we'll just subtract. Okay, and here we go. 720, let's try that again. 720 kilometers west. So this time, here's our starting point. And pretend I'm drawing good straight lines. 720 kilometers per hour west to our first stop here. Now, this says we're going backwards the opposite direction, east. So in this case, we're going to come back here, 83 kilometers per hour. Now, I could have said a distance of 83 and 720 also, but I chose, because we're talking about velocities, I chose kilometers per hour. What is the net velocity here? Are we going to add these? Well, since the east is opposite, then that means the 83 is now negative. So when I add these together, I got 720 plus negative 83. Or I could just change this to say minus 83 and then just do the subtraction. Because remember, adding a negative is the same thing as subtraction. So now I have 720 kilometers per hour west plus negative, or I could have said minus 83 kilometers per hour west. I highlighted the negative in the west. Oh, I see a mistake that, oh, nope, I got it. Because I said negative here, I can change that east to west. Because we're going 720 and back 83. And then that answer is 637 kilometers per hour west will be our net velocity. Takes a little getting used to when you haven't seen it before. But all we're going to do is either add if we keep going in the same direction, or subtract or add the negative if we're going in two opposite directions. Ready? All right, see that right triangle there? Right triangles should remind you of something. Let's say now we're here, we'll use the same numbers, but we start going 720 kilometers per hour east, and then we turn and go 83 kilometers per hour north. Now, if this is due east and that is due north, then we have a right angle right here. And that gives us a right triangle. And something I showed you a few minutes ago, right triangles should always make you think of something. One of your good friends, Mr. Pythagorean. If we have two dimensions and we make a right angle, use right triangle math, the Pythagorean theorem. We got the hypotenuse right there. Okay, therefore, 720 kilometers per hour east, and then go 83 kilometers per hour north. Now, since these are not the same direction, we can't just add those together and get 803. Where does 725 come from? There you go. All of you know the Pythagorean theorem. C squared equals a squared plus b squared. And I showed you that when I was talking about distance from home plate to second base. And then just fill in the numbers. 720 squared plus 83 squared. Do your math, and you'll end up at approximately, I rounded this off to the whole number, 725 kilometers per hour northeast. So if we started here, and made this trip, we end up right there. We ended up approximately, our net velocity, 725 kilometers per hour northeast of where we started. It's just a right triangle. It's just the Pythagorean theorem. Ready? You see on the graphs here, now on the recording, it may be hard to read those words on the graphs. So I'm going to go ahead and write up here. Okay, this is time on the x-axis. And on the y-axis here, this is position. So POS means position. And remember, velocity, okay, V equals D over T. Position is very much like a distance. And time, in this case, on the x-axis, would be the t here. So the velocity, remember in math, your slope is your difference of y over your difference in x. That's supposed to be a y there, so I'm going to redo that. I just wrote it too sloppy. Over your change in x. Your change in y is your displacement, and your change in x, in this case, will be the time that it takes. So it makes sense that velocity is distance over time. Now in 11C, the next set of notes, we're going to talk about acceleration. That's velocity over time. And acceleration is actually the change in velocity over a given time period. So the change in the velocities from maybe here to here divided by the time that it takes right there. And when we do assignments, we'll talk about that a little bit more. But everything we do relates to the XY graph that you're dealing with in your algebra classes. Ready? All right, last page if I remember correctly. Momentum. Every moving object possesses momentum, and that's because momentum is how much the object is moving. Not how fast, that's speed, but how much motion the object possesses. So there's your definition of momentum. The amount of motion in an object. This does have a formula also. Momentum equals mass times velocity. Now we use a lowercase p. I forget the word, but the Latin word for momentum begins with a P, and that's why we use a lowercase p. Equals little m for mass and little v for velocity. And if I know any two of those three variables, I can easily figure out the third. If I'm figuring out momentum, I just multiply the mass and the velocity. So let's say we're driving a car that is 1,272 kilograms, which is pretty close to the average mass of the normal vehicle, at about 29 meters per second, which is actually very fast. You're not used to the unit, may not seem like it, but that's a very high speed. Offhand, I don't remember the miles per hour, but it's booking it. So just multiply those together, and you get 36,888, and here's the unit, kilogram meters per second. And that little star up there on the computer, that's how we say times. All I did was multiply mass times velocity. So mass times velocity right there. Multiply the numbers together. Now if I know the momentum and one of these, I will simply divide to get the missing one. We're going to do that quite a bit in these physics chapters. Momentum is always conserved. Okay, we've talked before about different laws of conservation. Here's the law of conservation of momentum. The amount of momentum in a moving object is equal to the amount of momentum after a collision and the momentum transfers into other objects. So momentum is always conserved. Say you're hitting a baseball with a bat, the momentum of your bat before you hit the ball is equal to the total momentum of the bat and the ball after you make contact. And we'll talk more about that as practice problems come up. But momentum is always conserved. Same amount both before and after an event occurs. Ready? And that is all for sections 11A and B. The next time we'll talk more about acceleration. Deceleration is also considered acceleration. But that'll do it for now. We'll see you next time.